Hello and welcome to Math 355. This semester, we're going to be going through a bunch of content, and because I didn't feel that I could find a good set of videos for it online, I'm deciding to make my own. And so these lessons that we'll be going through are going to be very similar to the lessons which I would do in a traditional course setting. Today, we're going to be covering Chapter 1, Sections 1 through 3. And the good news about these sections is they're actually review material. As a prerequisite for this course, you should have taken intermediate algebra and trigonometry. And the entirety of Chapter 1 focuses on just reviewing Algebra 2 and trigonometry. And so we're going to go at a fairly quick pace through the Chapter 1 material. But if you have any issues, feel free to send me an email. We're going to begin with the idea of just some basic definitions. And so we have the idea of a function as well as relation. Functions and relations are really the core of what makes Algebra 2. And so Algebra 2 is the study of Algebra 1 material, but instead of dealing with the idea of expressions and equations, it focuses on this idea of functions. And so a relation is a set of ordered pairs. Any set of ordered pairs is fine. A function is a relation which assigns to each x value exactly one y value. What this means that you have a set of inputs and a set of outputs. When we're talking about functions or relations, the set of inputs, the set of x values, is called the domain. And the range is the set of outputs or the set of y values. Often when we're graphing things, we can think of a way of testing it as being the vertical line test. In that if you ever have the graph of something, let's just say that we have some arbitrary graph out here. Oh, let's see if I can make sure that that works. Cool. So let's stop the share real quick. And so if we have a graph of anything out here, this function, for instance, the vertical line test says that if we can draw a vertical line and it goes through more than one point on the graph, then it's no longer going to be a function. In this case, no matter where we draw a vertical line, it's only going to go through a single point. And so that means that this represents a function. If we had something which was a little bit more abstract, something like this, well, this graph is a relation, but it is very much not a function because we can draw a vertical line, and this vertical line would go through 4 different points. As soon as you're going through more than one point, it is no longer considered a function. Still a relation, but not a function. Sharing the screen again. We then have the idea of independent variables and dependent variables. And so the independent variable is the input and the dependent variable is the output. Typically, we're going to be dealing with variables of x or t for independent variable, while dependent variable, we're typically going to be using y or some function. One of the things which makes this calculus different from a traditional calculus like Math 400 is often in Math 400, you focus on the spatial elements more. And so you'd be using the x variable much more. Here, because we're calculus for biology and medicine, we're going to be focusing more on that time component. We're interested in things and how things change with respect to time, whether we're talking about population growths or really anything that's changing with respect to time. The spatial component, it's not going to be as big of an issue. It's mostly going to be that time one. That said, there are 4 ways that you can represent a function. One is verbally. And so for instance, if I were to tell you, for every input you give me the square of that value. That's a way of representing a function just verbally. And so in that case, it's going to be the squaring function. Numerically, using a table of values, we could also do. And so an example for the exact same function would be create a table of values. And we'll go with our standard x and y. If you give me a 0, 1, 2, 3, -1, -2, the squaring function would have given us a 0, 1, 4, 9, 1, 4. And so this table of values also represents a function because we have inputs and outputs. It's not as valuable as the putting it in words one though, because this one is really only telling us the inputs and outputs for these particular values. If I were to ask you what happens at 1.5, this version of that function will not tell you. Whereas if I tell you that we're squaring every time, well, then you'll know that what happens at 1.5. The next one is visually. And so we can use a graph to represent it. Graphing the squaring function is going to be our standard parabola. And hopefully you all know what the graph of a parabola looks like. That's a good approximation. Ideally, you want to make your graph look as accurate as possible. And so we want to put as many different points on here as possible. Usually I'll do an exercise or two where we actually just have you graph a million different things. We might do that later. But for now, just knowing the core shape of that graph is going to be important. The last way is algebraically. And so using an explicit formula. And so an explicit formula in this case could be something like y equals x squared. Y equals x squared would certainly work as the graph of that function, or as the equation for that function. And so these are really the four different ways that we can model a function. Most of the time, we're going to be focusing on the algebraic, but as we go on, we're going to be focusing a lot on the verbal, because there are some functions which are difficult to describe algebraically. And we'll see what those types of things look like later this semester. You can represent a relationship using the same methods. Do you know all the differences between a relation and a function? You guys totally know the difference between those two. You're great at this point. The next page focuses on exploring those ideas. And so the difference between relations and functions. And so we can model relations using something called an arrow diagram. An arrow diagram is something you typically do in Algebra 2. And it's really just a way of visualizing what relations look like and what they're actually doing. And so let's create an arrow diagram for at least this first example here. And then maybe we'll create our own example to try. And so for this first example, we're going to think of the relation 1, 3, 5, 7, 2, 3, and 3, 5. Now, to be clear, this is a relation, because all that a relation is a set of ordered pairs. And we could come up with it as a graph, but in this case, we're just doing a list of these ordered pairs. In order to create an arrow diagram for this, what we would do is we would consider all of the inputs and the outputs, and we would just show how they are connected. And so in this case, our inputs would be 1, 5, 2, and 3. And so we would say 1, 5, 2, and 3. Our outputs are 3, 7, 3, and 5. Since 3 is repeated, we would only show it once. And so they would be 3, 7, and 5. This is our inputs. This is our outputs. To make it an arrow diagram, then we just show how all of the inputs connect to our outputs. And so in this case, the 1 goes to 3. The 5 goes to 7. The 2 goes to 3. And the 3 goes to 5. There we go. This is the inputs, this is the outputs. We can use this to determine our domain and range. And so our domain in this case is just the input values. And so it would be the set containing 1, 5, 2, and 3. Because it's in set notation, the order doesn't matter. And so if you wanted to reorder these, that shouldn't be an issue. The range is then just going to be 3, 7, and 5. Now, the big question, is this a function? Yes or no? What do you think? While I wait for you to respond, knowing there will not be a response, in this case, this is a function. Notice that in this case, the inputs were not repeated. We had an output which was repeated, but that's okay. We just can't have any of the inputs repeated. Thinking of the vertical line test, if we were to plot these points, the 1, 3 and the 2, 3 would not be on the same vertical line. They'd be on the same horizontal line, but not the same vertical line. But really, we have all of these inputs, which are giving us outputs, and none of the inputs are repeated. If we ever have repeated inputs, that tells us that it is not a function. And so for our second example, I'll do over here, and we'll skip the middle one. Let's do this example here. The set containing 3, 7, 5, 6, 3, 2, and 0, 0. If you'd like, pause the video and see if you can go through this process of drawing the arrow diagram, stating the domain and range, and then stating whether or not it is a function. And then I'll do it on my end. And of course, since you paused the video, I'll just jump right in. So there's the domain and range, there's the arrow diagram. And now the big question, is it a function? And in this case, it is not a function. And the way that we can tell that this is not a function is we have an input value which is repeated. Really, we want to think of functions as working the way a machine would. And so for any given input, you want to know what your output is going to be. With this example that we had over here, for each input, we knew exactly what the output was going to be. With this example, though, if I gave you the input of 3, you could not tell me what the output was going to be because it's either going to be 7 or 2. And that's a problem. We want to make sure that we have one particular output. If we're trying to predict what's going to happen, well, having functions is kind of important. And most of the stuff we're going to be dealing with in this course is going to be functions, such as this one over here. But we are going to see a number of relations as well. There are a lot of complex systems when you're talking about medicine and biology, which do not adhere to functions. Oftentimes, you're not going to have guaranteed outcomes. And so it's important to understand what that looks like. That said, let's keep on going. Let's see if I can share the screen real quick. And we'll continue from there. And so tricks to tell if something is a relation or a function. Any rule that assigns numbers from one set to another is a relation. If that rule makes the assignment that no input has more than one output, then it's also a function. Any set of ordered pairs is automatically a relation. If none of the first coordinates are repeated, then it's also a function. Every function is a relation. Not every relation is a function. The next thing we have is graphing relations and functions. And so a graph is a way to visualize a collection of ordered pairs. Hopefully you all know how to graph since we've already done a couple of graphs. Graph the following equations. And with these, it's more just trying to understand the general shapes of objects. And again, these are kind of simplistic ones. And so y equals x squared. Hopefully we know the graph of y equals x squared. And if you want, there is a graphing utility which I would recommend, which might help with some of the graphs if you still struggle with graphs. It's good to be able to graph these things by hand, but Desmos is a free online tool which you can use to graph just about anything. And so in this case, we could say y equals x squared. And that gives us the graph of this function. It kind of gave that away. In this case, this is a function because notice for every x value, you're only going to get a single y value out of it. The next example is x equals y squared. What that is that's going to be the inverse of our parabola. X equals y squared. So notice this is now not going to be a function, because if we were to draw a vertical line, and let's even just write in a vertical line, x equals 2, notice that this is going through two different points on our curve. And so while this curve is a relation, it is not a function. The next example, I believe, was the absolute value. So the absolute value function, y equals the absolute value of x. Just type in ABS if you wanted to. Instead of being the nice curved parabola, we get a shape like this, which comes down to a point and then goes up. Again, this is just kind of one of the basic functions which you should know. It is very much a function. What's interesting is this and the other function, y equals x squared, they both have the same domain and range. And so the domain of both of these goes from negative infinity to positive infinity, while the range, the set of y values, starts at 0 and then goes off to infinity. And that's important to recognize. One of the things about calculus is you're interested in the shape of graphs. You're interested in how curvy things are, because we can have a lot of functions which are having very similar behavior, but we want to understand what exactly those differences are in the behavior. Another example would be something like y equals x. Y equals x, it starts at negative infinity, and goes to positive infinity. However, so would the function y equals x cubed. So with the equation y equals x cubed minus 3x. But when you look at the behavior of these two functions, it's very different. And so one question I could ask right now is, how would you describe the behavior of this function? And right now, we don't really have the tools to articulate that very well. We can say this is going up, and then it curves down, and then it curves back up. But we want to really talk about how it's curving. We want to talk about what the curvature of this object is actually looking like. Is it exponential? Well, not quite. Is it parabolic? Not quite. And so can we describe what the behavior of this object actually is? And calculus is going to give you the language of describing that. And that's going to be a very useful tool. The last example here is x plus y times x minus y equals 0. What do you think the graph of that is going to look like? And maybe we'll even graph this one by hand just to show you how weird it looks. And so x plus y this is probably the first example where I wouldn't expect you to have this one memorized at this point. So x plus y times x minus y equals 0. The thing about this equation is it's the product of two things being set equal to 0. And because of that, we can use the zero product property. The zero product property from back in Algebra 1 would say that either x plus y equals 0 or x minus y equals 0. Or if you prefer, y is equal to negative x, or y is equal to x. And those are two things which we should be able to graph very, very easily. And so in this case, the graph of y equals negative x is going to be coming down at an angle of 45 degrees, while y equals x is going to be coming up at an angle of 45 degrees. And so this equation should give us a graph which looks like this. Let's see if Desmos can do that. So pulling up our good friend Desmos, I want to do x plus y times x minus y equals 0. And notice it's able to graph it. One of the reasons I like Desmos is because it's able to grab a number of really abstract things which you would never be expected to graph, but sometimes you're going to be stuck with a really weird equation. In this case, this is very much a relation. The domain is still all real numbers, the range is still all real numbers, but it fails the vertical line test almost everywhere. This is a very simple example of something like this, though. If we wanted to see a more complex equation, I mean, there's a lot of complex equations out there. Let's see if I can do one of my favorites just off the top of my head. One of my favorites would be about absolute value of x minus 2. Then we'll square that. And then we'll do a plus y minus 2 squared. And then I'm going to do a minus, let's get rid of that thing, minus 4. And then let's multiply that by y plus the square root, SQRT, of 9 minus x squared. And then we'll set that equal to 0. Oh, I was off by a little here. This should have been minus 1. There we go. And now we get a nice little smiley face out of it. Again, we can determine what the domain and range of this function is. In this case, the domain would be everything from -3 to +3. The range would be everything from -3 to 0, and then from 1 to 3. In this case, it's very much a relation, very much not a function, but it's something which is just coming from a simple equation. And we can do a lot of different equations and get the graphs out of them. And Desmos will definitely help with you. If you wanted something more abstract than that, the trigonometric functions give you a wide variety of different things once you start mixing the x's and y's. So for instance, if we were to have a sine of x, let's go lowercase x, plus cosine of xy, let's make that equal to the tangent of y. We get a very interesting graph. And so now we can ask questions about this graph. What is the domain? What is the range? And how would you describe a graph like this? That's something we'll actually be doing in this class. And so we'll start to explore graphs like this and how we can describe what they look like other than abstract art. Yeah. And it's all going to be about trying to understand the rates of change and how we can determine what the rate of change is at all of the different locations on this graph. And this is definitely a very interesting signature. That said, we'll save that one for chapter 3, I believe. For now, let's get back to our standard lecture. Let's see here. Let's share the screen again. And so we already talked about the vertical line test. We know the vertical line test, no problem. And then we have the idea of the function machine. We talked a little bit about that. The idea that we want our functions to have inputs and outputs and to really work like a computer would work. And so for every input, you want to have a unique output. These 3 examples right here are just things which are a little bit more complicated to graph, but you should still be able to graph by hand if you wanted to. Let's try and do just this first one by hand and make sure that we know how to graph something like that. This one is a little bit beyond the scope of what you might see in an Algebra 2 course. If you take a college algebra, you might see it. We'll see things like this pop up throughout the semester, but not too many of them. You should still be able to graph them though. So f of x equals 1 over x squared minus 1. And we'll stop the share and we will graph this by hand. If you want to give it a shot and try and graph it by hand on your own real quick, go for it. And then we will compare what our by hand graphs look like. And then we'll compare it to what Desmos says the graph should look like. And it's good to start practicing drawing things by hand. There we go. And so our function is 1 over x squared minus 1. When we graph this, it might help to think about where the asymptotes are and then plug in some values. So in this case, looking at this, our denominator is going to have a 0 at 1 and at -1. That tells us that we're going to have vertical asymptotes at 1 and at -1. We could then ask what the long-term behavior is going to be. And if we plug in a number like a million bajillion into this equation, we're going to get 1 over a million bajillion squared minus 1, which is going to be something super duper tiny. And so as we go out to the right, we know that we're going to be approaching an asymptote which is at 0. Same thing to the left. If we plug in negative a million bajillion into this thing, we're going to get the exact same behavior, where this is going to be going back towards 0. Now we want to determine if things are positive or negative in each one of these regions, and also if there are any zeros. In this case, there are no zeros. There's no place where the numerator is going to equal to 0. So it's never going to actually physically cross the x-axis, but it may be bouncing down into different regions. And so in the center region, if we were to plug in 0, we would get 1 over -1, which is just -1. Since we know that this is not going to be crossing the x-axis, and we know that it's going to be approaching these two asymptotes, that tells us the graph is going to be coming up like this, and then going down like this. Out in this side, if we were to plug in a number like, let's say 5, we would get 1 over 25 minus 1, so 1/24, which is going to be a small number. This is telling us that it's going to be in the positive region, though, because it's a small positive value. So our graph is going to come down like this, cross here, and then approach this asymptote. Because this is an even function, we know it's going to be doing the exact same thing on the other side. But you could use the same logic of just plugging in a value to see what that looks like. I'm going to approach that asymptote. And this is a very rough approximation for what the graph should look like. I didn't actually plug in any values to plot points on the left or right side, but this gives us a pretty good idea of what this graph should look like. Let's compare our graph now to Desmos. And so let's see what Desmos says our graph should look like. Ooh, that's a beautiful graph. And so looking at our graph, and I will just make it so that it goes to the home, so it's centered. Our graph is f of x is equal to 1 over, and then let's say if I can actually do an x squared minus 1 there. And there's our graph. Notice that this has the asymptotes at x equals 1 and x equals -1. And it also has the horizontal asymptote at y equals 0. And so using those guidelines, we were able to figure out the graph pretty well. And the graph that we ended up developing looks fairly similar to that. And so I'm pretty happy with that result. The others that are here, this one is our standard semicircle formula, which you should remember from Algebra 2. This one's a little bit more interesting because this absolute value is going to be throwing things off a bit. And so the question becomes, what happens when you take a parabola and you subtract an absolute value graph from it? And think that over real quick, and then we'll graph it. And so an x squared, that's what x squared looks like. Y equals, let's say, the 2 absolute value of x looks like that. And when you subtract these two graphs, you're actually going to get a W shape. And you should ask yourself why that is. It really boils down to what the absolute value function is doing. because the absolute value function can be thought of as breaking the standard graph into two sections. One is this would be y equals 2x, but it's only going to be doing that when we have x being greater than or equal to 0. When x is less than or equal to 0, let's say f sub 2 of x, well, the x squared is going to be the same, but now for negative values, the absolute value of x is actually given by negative x. So it's going to be that when x is less than or equal to 0. And that's some interesting behavior. But that's what the graph of y equals the x squared minus the 2 absolute value of x looks like. It just comes from the original definition of what absolute value is. Well, one of them. Can we graph these functions? Can we find their domain and range? We absolutely can. Thinking of the equation that I did here, the domain for this one is going to be kind of interesting because the domain of this function is going to be everything from negative infinity out to -1, not including -1, in union with everything from -1 to +1, in union with everything from 1 to infinity. Another way of writing this is we could say that this is the set of all x element of the real numbers such that x is not equal to 1 or -1. It's kind of a clunky way of writing it, but it works. The range in this case would be everything except for this little gap here. So the range is going to be everything from negative infinity to -1. And we're actually including -1 in this because we can actually get -1 at this value. In union with everything from 0 to infinity. And we cannot actually get the 0, so we'll use a parenthesis there. So there's our domain and range. For the other one that we have, the one that we did on Desmos, our domain is all real numbers. And a range is going to be everything from -1 up to infinity. And so there's our standard domain and range stuff. The next subject we have is something which should have been introduced in Algebra 2 and in trigonometry, but there probably was not a substantial amount of context to it. But now that we're in calculus, we are going to be giving a lot of attention to difference quotients. In many ways, calculus is all about the study of difference quotients. And so we want to make sure we feel very, very comfortable with the idea of these things. And it's not even as much to calculate them as much as what these things represent. And in this case, we're going to have two different difference quotients, which we're going to be focusing on, for now at least. Later on, the tangent line difference quotient is going to be the one which you are going to be doing every single time. But for now, we want to understand what these difference quotients are and what they represent. Yeah, like I say, we'll be dealing with these a lot when we get to chapter 2, but mostly chapter 3. Chapter 3, 3.1 through 3.3, I think, are just exercises in difference quotients and understanding them. But what a difference quotient really is representing is a way of representing the slope of something which isn't necessarily a line. Let's pull up Desmos real quick so I can show you what I mean by that. And so if we think of the function f of x equals 3x plus 4, in this case, we can figure out exactly what the slope of this is at every single point, and it's not a problem. In this case, the slope is going to be just this 3 value here. And we could even just write it as m equals 3, and then we could just plug that into this equation, and this shows us that our slope is 3 all of the way through. Nice thing about Desmos is we could actually change what this is, and it'll show us in real time what that looks like. And so that's what it would be if it were 3x plus 4. But what if we were talking about the slope of a function like x squared? What does the slope of x squared look like? And that's something which is difficult to wrap your head around, because when we think about the slope, it's the rate of change. But in this case, the rate of change is no longer going to be a single number. And so there's two main ways that we can think about the rate of change. One is we can think about what the rate of change is as we go from one point to another point on this curve. And so let's suppose that we have a point x1 comma y1. And in this case, we'll even label it x1 comma f of x sub 1. And we'll create a slider for x1. What I did right here is I made it so that there's a point x1 f of x1 with the value of x1 being given here. And this is really going to be representing the x and y value, but the y value is coming from this function. And so as we slide this around, we can actually see that the point is going to be following that curve. Something to play with in Desmos. Well, if we have this being 1 point here, and let's just say that we're starting at -1, then we have this point at -1, 1. Let's create a second point. This time, again, we'll do the exact same thing, but now we'll make it x sub 2. So we'll make it x sub 2 comma f of x sub 2, so that it's pulling the y value from that equation. Well, now, again, we can change what this x2 value is. In this case, let's make it so that it's going out to 3. 3 might be too far. Let's make it 2. There we go. And so now a question could be, what is the slope going from this point to this point? That is what we call the secant line difference quotient. The secant line difference quotient, given at a point, f of x equals a, is given by this expression. Sometimes you're going to be given 2 values. Sometimes you're only going to be given one of the values. Sometimes you won't be given any of the values. And so be aware we have these different cases. Let's try this example here and see what it would look like. And we'll do it a couple of different ways. And so let's say that we have f of x is equal to x squared minus 4. And our secant line difference quotient formula, I'll write it up here so that we can see it once I take our shared screen down. Our difference quotient at point A is equal to f of x minus f of a over x minus a. And so let's suppose that we want to find, for part A, find the difference quotient from, let's say, a equals -1 to x equals 2. For part B, we'll just say find the difference quotient from a equals -1. And then for part C, we'll just say find the difference quotient. These are 3 different things you could be asked, and they each represent something slightly different. To show you what they represent, let's think of what the graph of this looks like. We'll do a very quick graph of this function. 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4, 1, 2, 3, 4. In this case, the graph of this function starts down here at 4. And then it would go up 1, up 2, And then the next one would be, let's see, that'd be 5. There we go. There we go. Make that dot bigger. And so for this first one, it's saying find the difference quotient from a equals -1 to x equals 2. And these are basically our starting value and our ending value. And so this is literally saying if we start at -1 and we go until 2, what is the slope of this? And notice this is just the slope equation in that case. And so for part A, we can really just calculate this straight away. Let's try the green pen and see if it works today. So for part A, we know that our x value is 2 and our a value is -1. Our f of x value, we could actually just come and look at the graph and see that it is 0. Because at 2, we could even say f of 2 is equal to 0. And at a, f of -1 is going to be equal to -3. And so now to find this difference quotient, all we have to do is plug those values into our difference quotient formula, which is just our slope formula. So our difference quotient is f of x, which is 0, minus f of a, which is -3, over x minus a. Crunching the numbers, we get 3 over 2 minus -1 is 3. And sure enough, we get a slope of 1. And looking at this line, yeah, of course it has a slope of 1. Notice as we go up 1, we go over 1, up 1 over 1, up 1 over 1, and that gets us the equation. And so in this case, the difference quotient is going to be 1. How this one differs from part B. Part B says find the difference quotient at a equals -1, but it does not give us an x value, which it's going to. And so in this case, we could be talking about the difference quotient from -1 to 2. But what if we were instead interested in going from -1 all the way up to here? So this would be at x equals 3. This was x equals 2. But what if x were equal to 1? What if x were equal to 0? What if x were equal to -1 or -2? And so what we're going to get when we do this one is we're actually going to get a formula in terms of x. And so let's calculate that out. And so for this example, part B, x we do not have. We do have a is equal to -1. We do know that f of a, in this case, is still going to be -3. But now all we can really do is plug it into this formula. And so our difference quotient is going to be given by f of x, which is this equation, x squared minus 4, minus f of a, which is -3, over x minus a, where a is -1. Now, this is a good start, but we definitely want to try and simplify this. And so let's see if we can simplify this a bit. Plus, 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 plus. We get x squared minus 1 over x plus 1. And sure enough, that numerator can factor. x plus 1, x minus 1. And that's going to be over an x plus 1. And then we can even cancel those. And we end up getting x plus 1 out of this. And so the question is, what does that x plus 1 actually represent? We'll write x plus 1 up here just so that we have it. Well, like we said, this is representing the slope. And so x plus 1 is representing the slope from a equals -1 out to any of these points. And so when x is equal to 3, remember that would be this line segment here, well, our slope, remember difference quotient is just slope, would be equal to x plus 1. That means that the slope here, oh, and I canceled very, very poorly. Whenever I'm doing these problems, make sure that you double check my stuff because I cannot be trusted. In this case, it's not going to be an x plus 1 because I cannot cancel. I mean, I meant to do that. I was testing you. Yeah, we're going to go with that one today. The x plus 1's cancel, and we're left with x minus 1. But like I was saying, that x minus 1 is corresponding to the slope here. I'll just write x minus 1 as our difference quotient. And so at x equals 3, well, our slope is going to be given by 3 minus 1, which is 2. And so the slope of this secant line is 2. When x is equal to 2, well, our slope is going to be 2 minus 1, which is 1. When x is 1, we get 1 minus 1, so our slope is 0. And again, looking at these, that looks appropriate. At this point, we'll get a slope of -1. At this one, we'll get a slope of -2. And then at this one, we'll get a slope of -3. And so that's what we get from this difference quotient, where we're actually given the a value, but not the x value. We're basically told where our starting point is, but we want to find an equation for the slope, which goes to any other point. For this third one, well, now we're not told what the a value is or what the x value is. The core difference in that case is now, instead of starting at our a equals -1 value, we could be starting at any value. And so this is the most general form. We could be starting at -2 and going to +3. Or we could be starting here and coming down here, or going across here, or starting up here. This is basically going to give us the equation for any secant line, the equation for the slope of any secant line. And again, we can find it just by plugging things into our formula. In this case, though, we don't have any of the values. And so for part C, all we can do is just plug things into our equation. And so our arbitrary difference quotient is going to be given by x squared minus 4 minus a squared minus 4 over x minus a, where this is the function evaluated at x, this is the function evaluated at a, and then we're just dividing by that bit in the bottom. From here, again, we try and simplify. And so we get our difference quotient is going to be equal to combining stuff. We can distribute that minus sign and get x squared minus a squared over x minus a, which is x plus a times x minus a over x minus a. And this time I'll cancel the correct ones, which gives us dq is equal to x plus a. Again, this represents the slope. And so this is telling us what the slope is as you go from any value to any other value on here. And it turns out you could just add the x components of the different points. And so on here, if we were going from -2 to a +3, because notice this is the x value is a -2 and a +3. Well, -2 plus 3 gives us a slope of 1. If we're going from, let's say here at 2 to 3, well, from 2 to 3, we could just add these two values and get that the slope is 5. And that's the power of this one. Basically, we've gone from the most specific idea of we know what both values are to the most abstract. And so with this most abstract one, we can find the slope connecting any 2 points on this curve. And it does not matter where those 2 points are, we can figure out what the slope of the secant line is. If I told you that we were going from, let's say, a starting value of -23, and we wanted to end at an x value of 100, I could tell you that the slope connecting those two is going to be equal to 100 plus -23, which, seeing if my math brain is working, is 77. So even without looking at the graph, even without knowing anything, even without plugging in any values, we're able to figure out what the slope is connecting those 2 points. And that's the power of the difference quotient. Like I said, we have 2 difference quotients. The secant line difference quotient, which is what this one is probably the easier one to visualize. Because when we think about this one, really what we're doing is we're just going from one point to another point. The problem is it's actually not as valuable because typically we want to figure out what the tangent line is using a single point. And that's where the second one comes in. The second idea of the difference quotient is the tangent line difference quotient. And we'll be using that one much, much more. And so let's see if we can see what the visual for that one looks like. And we'll do the exact same formula. The difference quotient in this case, we will not be dealing with h and x. And so we'll replace that. But let's just write out our difference quotient formula. So our difference quotient formula now for the tangent line difference quotient is f of x plus h minus f of x over h. And let's see if we can understand the visual for this one. And we'll use that exact same function, x squared minus 4. And so let's start with the graph of this. And so when we are graphing x squared minus 4, again, we'll graph it really quick. 1, 2, 3, 4. Counting is probably the hardest part of this teaching gig. 1, 2, 3, 4. Our graph, we know the graph of this one. We should be able to do it blindfolded, though I would not recommend graphing while blindfolded. There we go. And we'll move that one over a little bit. There we go. And a little bit steeper there. There we go. That's a decent graph of it, not perfect. And so just like before, this is representing the slope as you're going from one point to another point. What's different is in this case, instead of starting at one point and then using another point, we're actually going to begin with a single point, and then we're going to ask how far are we running from that point. And so in this case, the h value is really representing the run in our rise over run. And so if we were to begin at an x value, in this case, of -1, x equals -1, then that means we're starting right here. Well, instead of saying that we're going to be going to a different x value, we're going to say that we're going to run across this graph a certain number of units. And that's where we can get a second point. And so our second point isn't coming from me telling you we're starting at 2. Instead, it's telling you we're just going to be going 3 units to the right. And so for these difference quotients, instead of given the 2 points, we would say find the difference quotients where, let's say with x equal to -1 and h equal to 3. Or we could say find the difference quotient with x equal to -1. Or we could just say find the difference quotient where we're not given any of the information. And let's see how this formula is going to give us something different but very similar to the other one. And so in this case, let's start with A. Again, we're just trying to find the slope connecting these two. And from the last example, we already know what that slope is. But looking at this one, if we know that x is equal to -1 and h is equal to 3, then f of x is very easy to figure out, because f of x is just going to be plugging -1 into this equation, which is going to give us -3. Our f of x plus h is really going to be f of 2, because -1 plus 3 is 2. And when we plug 2 into this, we know that we get 0. Now we can plug it all into our formula. And so our difference quotient, as we're going from -1 and we're running 3 units over, it's going to be f of x plus h, which is 0, minus f of x, which is -3, over our h value, which is +3. And sure enough, simplifying that, we end up getting 1 out of it. So notice, even though we're using this different approach, we ended up getting the exact same slope for this, which makes sense because we shouldn't get any other slope for it. The second one, though, is going to be different. Find the difference quotient with x equal to -1. Again, in this case, we're not going to be restricting what our h value is. And so now our h value could be just about anything. What if instead of going 3 units over, we were just going 2 units over? Well, then that would give us this slope. Or what if we were going 3 units, or what if we were going 4 units over? That would give us this one, or 1 unit over. And so much like before, we're getting all of these different paths, but now instead of saying what's the x value you're ending at, we're saying how far are we actually going from our starting value. And so our equation is going to be a little bit more complicated. And so for part B, our difference quotient is going to be starting at x equals -1. And so we know x equals -1. We do not know what h is. We know f of x is equal to x squared minus 4. But now we need to figure out what f of x plus h is. And this itself can be a little bit of a challenge. So f of x plus h in this case would be f of -1 plus h, which would be equal to -1 plus h squared minus 4. Basically, wherever we had an x, we're replacing it with -1 plus h. And so that's where we get this from. The x and -1 plus h, they match up exactly. Now we're just going to be replacing this whole thing, or sorry, not replacing. We're going to be simplifying this expression as much as we can, because we don't really want to plug this into this equation. That's not going to be very nice. Oh, and I should have simplified this one too. Our f of x, we knew that f of x was equal to x squared minus 4. And so that means that we would need to know what f of -1 is. -1 squared minus 4. And negative 1 squared minus 4 would give us a negative 3, because that's 1 minus 4 is negative 3. For this one, when we simplify it, well, we can FOIL this thing. Negative 1 squared is going to be 1. We're going to get h squared, which is h squared. And then we're going to get negative 1 times h plus negative 1 times h, which is negative 2h, and minus 4. For those that don't know where that negative 2h came from, see if you can FOIL negative 1 plus h times negative 1 plus h. When you do that, you'll see that negative 2h come out of it. But now we can simplify this, which is going to give us an h squared minus 2h minus 3. And so now we have all of the different components. We have our f of x is equal to negative 3. That'll go there. We have our f of x plus h is equal to this thing. That'll go there. And then we have our h, which is just going to be hanging out. And so now we can plug all of these things in. And that will give us our difference quotient, which is going to be f of x plus h, which is h squared minus 2h minus 3, minus f of x, which is negative 3, over h. Now we want to simplify it. When we simplify this thing, h squared minus 2h minus 3 minus a negative 3, the 3's are going to cancel out, leaving h squared minus 2h over h, which then we can cancel the h's out by factoring and canceling, which gives an h minus 2. And that's going to tell us what our slope is at every single point. And so no matter how far we're running, we know that the slope is always going to be given by h minus 2. And so let's say that we were dealing with this first one. Well, this first one that we did was h equals 3. According to this formula, our slope is going to be given by 3 minus 2. And 3 minus 2 is 1. If we were to go up to this one, well, now our h, how far we're running over, is 4. And using this equation, 4 minus 2 tells us that our slope is going to be 2. If we go backwards, that's going to tell us that our h is going to be equal to what it's called, negative 1, because we're going backwards. And on that case, our slope is going to be negative 3. And so far, this is much the same as what we did before, right? There's nothing really that different. Here's where the value of this one comes in. And so with the other one, really we needed to have 2 points even to start defining the thing. In this case, we don't really need 2 points to define our starting and our ending. And instead we can think about a starting point and how far we're running from it. If we were to let this h value get arbitrarily small, and so if we were to let this h value go to 0, and this is something we'll be doing in chapter 2. Well, as h goes to 0, these curves, these lines that we've drawn in here, are going to get closer and closer and closer to our starting point, until eventually we're going to get something called the tangent line. Let's see if I can actually draw it in here a little better. And so this would be a line which is only touching at this one point. And that's called the tangent line. The tangent line occurs when our run becomes 0. Now we can't plug h equals 0 into our starting thing because we would be dividing by 0, and we're not allowed to divide by 0. But after we've simplified this whole thing, we can ask what happens as we get arbitrarily close to 0. And then it's basically like plugging 0 in. That's called a limit. And again, that's what chapter 2 is all about. But we can plug that in here and we'll get our difference quotient is equal to 0 minus 2, which tells us that the slope here would be -2. That is very, very useful information. And let me even show you why that is useful information. Well, maybe I'll show you after we do this last example. Because this difference quotient is telling us what the slope is at a particular point. But we still have this case of, what if I didn't tell you that we were starting at this point? What would that look like? And much like before, if we were to do that, well, now instead of choosing a particular point to start at, we could say, what if we start here? And we want to figure out the slope from here to everywhere based on this h equals 0 thing. And we can solve that one too. And so for number 3, oh, and I'll write up here, the answer we got was h minus 2. So if we're not told what x or h are, then all we can really do is just plug things into this formula and hope for the best. And so we know that f of x is equal to x squared minus 4 for part C. And f of x plus h is going to be equal to x plus h squared minus 4, which we could clean up if we wanted to and make it x squared minus 2xh. Oh, and this was a plus. Sorry about that. I've been so bad with signs today. Definitely double check everything I do. Plus h squared minus 4. And once we have that, we can plug this and this into our starting difference quotient. And so our new difference quotient is going to be equal to, what would that be? That would be x squared plus 2xh plus h squared minus 4 minus our f of x, which is x squared minus 4, all over h. And now again, we're going to try and simplify this. Typically with difference quotients, your goal is to get rid of that denominator at all costs. And we should be able to do that here. And so in this case, we can clean up the top by canceling out the x squareds and canceling out the 4s, leaving us with a 2xh plus h squared over h. And those h's cancel, leaving 2x plus h. And that's our answer at that point, just 2x plus h. Because we get to cancel out, or we factor out the h, and then we cancel the h, and we get 2x plus h out of this. This right here will tell us the slope as we're going from any starting x value out h units. And as I said before, what's special about this is we could find the instantaneous rate of change. I'll just write that here, instantaneous rate of change. Which is the slope of the tangent point by setting h equal to 0. And that's very useful. That's what chapter 3 is all about. Chapter 3 is all about finding this instantaneous rate of change. We actually call it the derivative. But if we set h equal to 0, that tells us an equation for the slope at every single point. And let me show you what that looks like in our good friend Desmos. And so let's create something very similar. And so we'll say f of x is equal to x squared minus 4. We will create a point on this graph given by x1 comma f of x1. There we go. We'll create a slider for x1. So now we can move this point wherever we want. We can create the equation of a line going through that point by saying y equals mx plus b, but it might make more sense to use the point slope form. So point slope form would be y minus our y1, which is f of x sub 1, equals m times x minus x sub 1. Now the only thing we need is we need to know what the slope is at that point. And let's make this green. Because if we knew what the slope was at this point, then we could get something which is tangent. But it would be tangent no matter where we are on this curve. So once we set that m equal to 3.1, we'll notice it's no longer going to be that slope at all of these other points. The equation we just found, where we set h equal to 0, would be 2x. And so if we set our slope to be 2 times our x value, then this is now going to give us the tangent line at every single point. And that is very, very, very useful. When we think about what calculus is all about, this is really the fundamentals. This is what makes it so that we can do just about any differential equations. Anytime we're dealing with populations which are tied to their rates of change, the most basic example being bunny rabbits. The more bunny rabbits you have, the greater the growth rate is going to be. Well, we can now tie our rates of change to our starting functions. And that is fundamental for everything we're going to be doing in this class. For now, though, you just have to make sure that you know how to evaluate these things. But to show how abstract things are going to get, we actually use the notation with an apostrophe to represent the rate of change. And with this, we can now figure this out for any function we want. Like, let's say that we had an x cubed minus a 2x like we were doing before. This is, again, going to just follow this curve exactly. We could make it something trigonometric. Sine of x. And it's going to follow this exactly. We could make it so that it's something more abstract. How about a sine of x squared? It's harder to see, but it's following this exactly. And it doesn't matter how complicated a function we get. And there are some very complicated functions out there. How about an x times sine of 100x? This is a very complicated function. But this equation that we have down here is actually going to tell us the equation, which is tangent at every single point. Now, the challenge is we have to be able to find the difference quotient of this function. And right now, we do not have the tools to do that. We will have the tools to do the difference quotient of that starting in chapter 3. And so definitely get prepared to start playing with difference quotients, because we're going to be playing with a lot of difference quotients this semester. For now, though, all you need to know is these two formulas and how to evaluate them. And as long as you can evaluate them, you're going to be in good shape. The next topic, might need to go run and take a break, but the next topic is piecewise defined functions. And again, this is something which you should be familiar with from Algebra 2. A piecewise defined function is a function which is defined differently on different intervals. And I give a couple of examples here. In this case, g of x is equal to negative x on negative infinity to 0. And then it's 1 minus x squared on 0 to 1. And then it's x minus 1 on the interval from 1 to infinity. What this is really saying is we're going to have 3 different functions, which are basically grouped together to create a single function. So let's see if we can graph this function real quick, and then we'll do domain and range for it. So g of x is equal to, and I'll just copy this down on my whiteboard, and then x minus 1, negative infinity to 0, then on 0 to 1, and then on 1 to infinity. Cool. And this one had a bracket right there. Cool. So let's see if we can graph this thing by hand, because it is good to practice graphing things by hand. 1, 2, 3, 4, 1. Well, I can do better than that. One thing you'll notice is that I am very particular about graphs. 2, 3, 4. That's good enough. And so in this case, we have 3 functions, which are grouped together. And what makes it piecewise is really we just do it one piece at a time. Over here on the right side, it's saying what the domain is that we're actually playing with that function on. And so for the first one, it's -x. And so it's -x on the interval from -infinity to 0. And so on the interval from -infinity to 0, we know we're dealing with the equation y equals -x. On the interval from 0 to 1, we're going to be dealing with the equation y equals 1 minus x squared. And then from 1 out to infinity, we're going to be dealing with the equation y equals x minus 1. And now we just have to graph it. And so from -infinity to 0, including 0, we're going to be graphing a line which is y equals -x. And that's the graph of y equals -x. From 0 to 1, we're going to have 1 minus x squared. Notice it's not including 0 though. And so when we plug 0 in, we get 1 minus 0 is 1. But since we're not including that point, we're actually going to use an empty circle there. At 1, 1 minus 1 is 1. And then this is a parabola, and it's going to be an upside down parabola. There we go. And then the next one, it starts at 1, but notice it's not including 1, so we might have to use an empty circle. But when we plug 1 in, 1 minus 1 is 0, and that would actually be starting at this point. Since it's starting at that point, we don't actually have to draw the empty circle, because we know at 1, we're going to get that value. And then it has a slope of 1. And so this is the graph of this function. We could find the domain. In this case, we can plug any real number into this. We can find the range. We can get any value of 0 or larger. And so our lowest value is 0. And then it'll go to infinity. And that's our domain and range. Hopefully that all makes sense as I sip some water. Cool. And so that's the idea with a piecewise defined function. We can find domain and range, we can evaluate them, we can do all of the same things that we do with functions. The next thing is something which is going to be possibly the biggest challenge of the week. And that is make sure that you know your functions. And so here is the set of functions which I expect you to already know like the back of your hand. You should not have to think twice about any of these functions. You should know what the graphs are. You should know how to evaluate them. You should know everything about these functions. And so linear functions, parabolas or quadratic functions, polynomial functions, reciprocal functions, any type of rational function. Rational functions, you know, those can get very tricky because those are more of a college algebra thing, but you should have had some graphing experience with these in Algebra 2. The absolute value functions, the square root functions, any radical functions, exponential functions, logarithmic functions, circles, semicircles, ellipses, hyperbolas, and your core trig functions. You should know all of those functions. The only ones where it might be a little tricky is finding range for polynomials and general rational functions. That's something we will do in chapter 4, I believe. But make sure you know all these functions. And if you don't, hit the books and start studying, because we are going to be playing with all of these functions. Trigonometry and algebra kind of give us the tool set for everything we're going to be doing in this course. And we'll explain why that is later on. But we're going to be playing with all of these functions. And not only are we going to be playing with these functions, but we're going to be playing with the compositions of these functions. And so what would a graph like this look like? Let me do something like this. If I asked you to graph f of x equals the sine of the natural log of the absolute value of x, could you tell me what the graph of that function is going to look like? We're going to be dealing with functions like that. And at this point, I don't expect you to have all of the answers of what the graphs of these things look like. But we're going to be seeing stuff like this pop up very, very soon. If I had to do a quick guess as to what this looks like, and again, this is going to be a very, very quick guess, I would guess that we are going to get something which is going up and down to 1 and -1. It is probably going to look like hell on wheels between -1 and +1. And then it's probably going to smooth out quite a bit. It should still be oscillating, but probably not as much. So here it's just look thick. And then by the time we get here, it should start to slow down a bit. It'll probably just go very slowly. And then it'll probably just go like flat, either on the top or the bottom. And same on the other side. And then it'll just kind of slowly. It's an even function, so it should match the left side and the right side. As far as whether it looks like it's on the top or bottom, I'm not sure. But hey, we have a tool. And when in doubt, always go to Desmos for these things. And so let's see what the graph actually looks like for this function. The graph would be f of x equals sine of the natural log of the absolute value of x. And there we go. And so it looks like it's not even between -1 and 1 that it's going to look that bad, because it's going so fast that you're not even going to see it. But notice how there are an infinite number of these oscillations between here. It is ridiculous how fast this is going to go. Let's even go home, and then let's just zoom in on this as much as we can. And you'll see that we have oscillation after oscillation after oscillation. There are an infinite number of oscillations as you zoom in on this. And then as you zoom out, well, notice it starts to flatten out a bit. And then if we keep going out here, it's going to get slower and slower and slower. But it is actually going to have an infinite number of oscillations out here as well. We can actually change how far we're going. Let's set this x-axis to start at 0. And you might hear a crying baby in the back. She is now 2.5 months, so hopefully she won't give too much trouble. But as we go out and out, I'm just adding zeros here. So 10 to the 6th, 10 to the 7th. You can see that this is going to continue to oscillate infinitely, but it's going, it takes so long for it to oscillate at this point. From here to here is going to be roughly 4 with 32 zeros after it. That is a tremendous amount for a single oscillation. And so that's the type of thing that we're experiencing with a function like this. And we're going to be seeing lots of weird functions like this pop up throughout the semester. And what we want to do is we want to know what the behavior of these functions actually is. And the first step to knowing that is to knowing what the general behavior of these functions are. You should also know your inverse trig functions, but we'll be going over them again next lesson, I believe. For now, this is what our core functions look like, so make sure that you feel comfy with them. Yeah, definitely put in some time if you don't feel comfy with them, because they are going to be popping up a lot. We also have all of the function transformations. And so we want to make sure that you feel comfy with all of the different transformations. This will help you when you're trying to deal with compositions as far as how different functions are being manipulated. And so for instance, if you have f of x plus k, that moves the graph up k units. If it's a minus k, it goes down. If something's happening inside of the argument, we're going to see a minus h or a plus h. Well, minus h will move the graph to the right h units. A plus h moves the graph to the left h units. We can then flip it using negative signs. And so a negative f of x flips the graph across the x-axis, while f of negative x flips it across the y-axis. We can then manipulate the speed of these things. And so a times f of x, anything outside of the function, is going to modify how it's looking vertically. If it's on the inside of the function, well, that's going to modify how it looks horizontally. And the graph of af of bx minus h plus k combines all of those properties. The one in here which is most confusing for folks is probably the horizontal. Large values of b make it look skinnier, and small values make it look wider. The reason for this is we really want to think of this b value as kind of modulating the speed of it. And so the b value in here is telling you how fast or slow you're going with the graph. And if you're going faster, then the graph is going to be done in a shorter amount of time. If you're going slower, then it's going to be done in a fraction of the time. And so you want to make sure that you feel comfy with that. Again, with Desmos, we can actually visualize this. And so let's create a function. How about f of x equals, and then let's make it, how about square or x negative x squared. And then let's do a shifting of it 2 units to the right. And then let's shift it 4 units up. And then let's make it so this is only going to be defined from 0 to 4. That gives us this interesting curve. And I kind of like this curve because it has a very fixed domain and range. Our domain is 0 to 4, our range is 0 to 4. And now we can ask what happens when we start to manipulate this graph. So if I were to give you y equals, and let me even just hide this graph real quick. If I gave you y equals 2f of x, well, what this should do is this should make it so that the graph is going to be doubled in height. There we go. And now we can try all of those different function manipulations. And so we said if we add a k value, so if we were to add 3 to it, that's going to shift the graph up 3 units. If we made it a minus 3, that's going to shift the graph down 3 units. If instead we take the 3 and we put it on the inside, and so if we add 3 in here, it should shift the graph to the left. If we make it a minus 3, it's going to shift the graph to the right. If we put a minus sign in front of this graph, that's going to shift, or that's going to flip it down. If we put a minus sign inside, that's going to flip it across. If we put a minus sign in both, well, now we're going into quadrant 3. If we have a multiplier in the front, like 3, this is going to make it so that it's 3 times as tall. If we make it a fraction, like 1/3, that'll make it 1/3 the height. The tricky one is when we modify the inside. And so if we put a 3 inside, that's going to make it go 3 times as fast, which means it's going to be much skinnier. If instead we made this a 1/3, then it's going to be going at a fraction of the speed, which means it's probably not going to be done until 12. There we go. And now we can apply all of these different function manipulations if we want to. And so we can make this a negative 2f of, how about 1/3? And then we'll make it an x minus 3. And then let's throw a plus 7. This function and this function still have a very, very similar structure, but it's just been manipulated. And so we flipped it, we've stretched it out a whole bunch, but fundamentally, these are very, very similar functions. Hopefully that helps. If you want, here's another practice problem where you can take this function and you can try and do all of these different function manipulations to it. You should be able to do it by hand without too much trouble. But if you want, you can go to Desmos and play with these functions. The last page of our lecture today, and again, we're trying to cover chapter 1 as quick as we can, but we are going a little long here, is just focusing on the idea of compositions and some of the different function operations. And again, this is very much an algebra 2 thing. The idea where if we have two functions, we can add the functions together, we can subtract them, we can multiply them, we can divide them, or we can do the composition. Composition is the big one. Composition is where we take one function and we plug it into another function. And so let's do an example. These are kind of boring examples. Let's do a fun one. So let's say that we have f of x is equal to sine of x. Let's say that g of x is equal to 2 to the x. And let's say that h of x is equal to, how about the square root of x? Then if we were to just add functions, well, that's no problem. We could do f plus g, f of x plus g of x, which is sometimes written as f plus g of x. This would just be adding the two functions together. And so we get sine of x plus 2 to the x. Done. Composition, though, is where we take one function and we plug it into the other function. And so, for instance, if we were to do f of h of x, what this really means is this means f of h of x, where you take the h of x and you plug it in everywhere where you have an x in your function. And so in this case, it would be sine of square root of x. Now we can do multiple of these if we wanted to. And so we could do g of f of h of x. In this case, that would be saying we're going to take our h function and plug it into f, which we've already done. And then we're going to take all of that and plug it into our g function. And so this would be g of f of h of x. In this case, we already have f of h of x is sine of square root of x. And so g of f of h of x would be 2 to the sine of square root of x. And this is now just a new function. Here's the question. What's the domain? What's the range? And what's the graph look like? At this point, I don't expect you to have those answers, but you should start to think about what this graph would look like and try and do it by hand without actually using a graphing utility. Try and think about how all of the different components of this function interact with one another. For instance, when we think about this function, I would start by just looking at what the most restrictive components are of it. And thinking of this function, if we were to try and do just something very basic, we know that our sine component is bounded between -1 and +1. And so whatever's happening in this graph, we know that this is going to be bouncing between 2 to the -1 and 2 to the +1. And so 2 to the -1 would be 1/2. So we'll put a 1/2 dotted line here. And we'll put the 2 up here. Whatever is going on with this function, we know that it's going to be bound between these two. We also know the square root of x is only defined for positive values, which means that we're not going to have anything negative going on here. At that point, we could just start plugging in some values. We know that at 0, we're going to get square root of 0 is 0, sine of 0 is 0, and 2 to the 0 would be 1. Sine is generally going to be increasing, and so as the square root increases, sine is going to increase and then decrease. But what's interesting is this is actually going to be kind of stretched in a weird way. We could think of our sine as coming up here or coming down, but it's going to actually go down a very small amount, and it's going to take longer and longer and longer. The distance from here, or the period, is going to get longer and longer and longer the further out we go. And so this is a rough estimate for what our graph might look like for this one. Let's take a look and see how close we were. So in this case, it was 2 to the sine of square root of x. And notice we're getting that type of behavior out of this thing. And so it starts here, and let's even just draw the line y equals 1. So you can see that it starts by going up and down, then it goes down and up, then it goes up and down again. And it's going to continue this pattern on and on. But the distance it takes to go from 1 to 1 is going to get longer and longer and longer. That's the type of thing you want to start practicing. You want to start practicing recognizing how these compositions of functions interact with one another. And you could just use Desmos and play with it a bit. Desmos actually has the ability to do compositions of functions. And so we could say f of x equals, what was f of x? I already forgot. I think f of x is our sine function. And then h of x was our square root function. Then g of x was equal to our exponential function. And we could say g of f of h of x. And it will graph this function for us. But then the question becomes, what about other compositions? I want to do y equals that. Because there's a lot of different compositions that we could do. What if we did sine of 2 to the x? What would sine of 2 to the x look like? Well, that would be f of g of x. What if we were to be doing the square root of sine? What if we were to be doing this 2 to the sine? I mean, there's a lot of different functions that we can start composing. And once we get to chapter 2, we're going to start playing with that idea of composing these weird functions. Things are going to get very, very weird, and then we're going to try and figure out the rates of change of those weird functions. And really, any function that you've seen up to this point is fair game. So all of the algebra functions and all of the trigonometric functions, we're going to be dealing with all of them. The last piece here is just a few definitions. And so a function is even if it has symmetry across the y-axis. It's odd if it has symmetry across the origin. It's periodic if it has a fixed period where it's repeating. Increasing means the graph is going in an upward direction as you go to the right. Decreasing means you're going in a downward direction as you're going to the right. And that brings us to the end of today's lesson. We covered a tremendous amount of material, but in theory, all of this material should have been reviewed. The main exception being we went a little bit more in depth into difference quotients. But I highly recommend you go through and practice some of these problems that are in this lesson plan. And if you have any questions, feel free to email me. You have a ton of homework ahead of you. And so the sooner you get started on that homework, the better. But for now, I will leave you with this. Let's see.